Welcome to section 9.2. In our first lesson today, we're going to talk about angles that are in standard position, and we're also going to be introduced to radian measure, and we're going to convert from degrees to radian measure. In our second lesson, we'll talk about arc length and area of a sector. We're going to begin studying angles today in perhaps a little bit different fashion than we have in geometry. We're going to be looking at all sorts of angles. Angles exist everywhere. There's an example here of one on a windmill, but take a look around. You'll see angles everywhere. It's impossible to not see angles with your eyes open. Let's see what angles are made of. They're created with two rays that share a common vertex. So we have ray 1, ray 2, and we have a vertex. But they can spin, they can be anywhere throughout the world. And so in order to analyze them a little bit more carefully throughout the ages, we've decided to place them in the coordinate plane, a two-dimensional plane for a two-dimensional figure, an angle. To get a little bit more careful, we decide to place the vertex always at the origin, at 0, 0. So one of our three components, the vertex, is always in the same location. That helps things to be a little bit better systematized. And then also, we take one of those two rays and always put them in the same position, what we refer to as the initial side, or the initial ray. Notice on the right-hand diagram here, the light blue ray has the origin as an endpoint, and then it goes out along the x-axis in the positive direction. That only leaves the third piece, the second ray, to be able to shift over to wherever position it needs to be. The diagram is showing an obtuse angle. It could be acute, right, straight, but you might notice that because we can rotate forever, angles can be greater than 180 degrees. They can be a full circle. They can even be more than a full circle. You can imagine a tire spinning around on a car going much more than 360 degrees as you travel down along the road. And if you think that you can go in reverse, you can also go backwards, and we can have negative degrees. But in order for us to be able to study these a little bit more carefully, we're going to have to get familiar with standard position so that we can see where the terminal side will end. So here's just a nice diagram of angles that are in standard position. The initial side is always along the x-axis, the vertex is always at the origin, and then it's just a question for us as to where does the terminal side end. Most of the time, we live in the world of the first quadrant in real life. There's obviously the first, second, third, and fourth quadrants. The first quadrant is where everything is positive. So if we have our initial side along the x-axis and we want to live most of the time in the first quadrant, then when we go up into the first quadrant, those are going to be positive angles. Well, that means if you can see the way the arc is rotating here, this red arc, it's telling us that positive angles rotate counterclockwise. Therefore, negative angles rotate clockwise. And we don't need to restrict ourselves to being in the first quadrant. We don't have to restrict ourselves to a protractor and having just simply up to and including 180 degrees. We can have an infinite number of degrees. We are only seeing increments of 90, 90, 180, 270, 360, but we can go to 450 and 540. We can have 720 degrees. We can have 1,000 degrees. We can have negative 422 degrees if we want. In order for us to locate these, we're always going to begin at the initial side and then rotate in the proper direction with the correct number of degrees. Our first example today challenges us to draw angles with the given measure in standard position. 390 degrees, negative 160, and 690 degrees. Take a moment to try these. If you want to pause the video, feel free to do so. Remember that there are 360 degrees in a circle, and we're asked to draw 390 degrees. So how do we do that? Well, we begin with standard position, so we begin with one of our rays on the x-axis, and we start to go counterclockwise, and a full circle would get us back to the x-axis, and then we need to go an additional 30 degrees. So our angle ends in this position in the first quadrant, where we have rotated a full circle plus an additional 30 degrees to get us to 390. For the second one, negative 160 degrees, we are going to again place our initial side along the x-axis. Because of the negative, we're going to go clockwise, so we're going to drop down into the fourth quadrant immediately. To go negative 90 degrees would get us down to the y-axis. To go negative 180 degrees would get us back up to the x-axis. We only want to go negative 160, so we will be 20 degrees shy of coming up to the x-axis. We will live down there in the third quadrant. When we want to go a positive 690 degrees, we're going to go back to the counterclockwise motion, and to go a full circle is 360. To go two full rotations would be 720 degrees. We are 30 degrees shy of making two full rotations. So you might look at that and see that as a 30-degree angle, which would be accurate, but we are terminating there. We are finishing up our angle by going one full rotation and then just 30 degrees shy of a second full rotation for 690 degrees. Notice that we could have gone in that second picture, take away the arc, take away the notion that it's negative 160. Do you notice that if we went a positive 200 degrees, we would start at the x-axis, go counterclockwise through 180, and then go an additional 20 degrees down to get us to 200? If 200 degrees and negative 160 degrees end in the same location, those would be said to be coterminal because they end in the same location. So co meaning same, terminal ending point. If angles ever end in the same location, they are called coterminal angles. If we can rotate around a circle more than once, if we can have angles that are greater than 360 degrees, then it's going to be increasingly important for us to be able to find these coterminal angles. And so in example 2, we're asked to find two examples of angles that are coterminal, one positive and one negative. If we take negative 45 degrees, notice that we rotate down into the fourth quadrant. If we're to find one positive angle, one way to do that would be to say, what is negative 45 plus 360? And we could come out to 315 degrees. We could have also added 720. We could have rotated two turns and come up. There's an infinite number of possibilities. If we want to know one negative angle that's also coterminal with negative 45, we could subtract 360 and get negative 405 degrees. For 395 degrees, you see that we've rotated around a full circle and then we've come up another 35 degrees. If we want to know what's another positive angle, we could add 360, or we could subtract 360 and come out to 35 degrees. There's an infinite number of possibilities, but generally we tend to like to have our angles within 360 degrees. So a negative angle, we could either take 395 and subtract 720, or if 35 is coterminal, we could subtract 360, and negative 325 is another good example. In general, if we take our angles and add or subtract multiples of 360, so 360 times n, provided that n is an integer, we will come out with coterminal angles. Now we're going to be introduced to a new unit of measure called radian measure to help us measure angles. We start off by looking at a circle, and let's say for this circle the radius is equal to 1. Do you remember the circumference of a circle? The formula equals pi times the diameter, or 2 pi r. But let's just say pi times the diameter for a second. If the radius equals 1, then the diameter equals 2, and the circumference would be 2 times pi times the diameter, so 2 pi. That's going to get us over into the unit circle. Unit meaning there's a radius of 1. If the word radian sounds a lot like radius, it's because if the radius equals 1 unit, then the arc length of 1 radian is going to equal the radius. From the x-axis going up to where it says 1 radian, that arc length is the same exact length as the radius 1. You'll notice that that comes out to about 57.3 degrees. Well, if we were to double that and go to 2 radians, or 3 radians, 4, 5, 6 radians, you could see how we could continue to go around. And so we could have 7, 8, 9, 10, we could have infinite radians, and we can have negative radians, the same way we can work with degrees being positive, negative, and going around the circle more than once. So why is this beneficial? Why is this a nice thing? And it doesn't look like 3 radians doesn't quite get us down to the x-axis, 6 radians doesn't get us back up to the x-axis. So why is this beneficial? Well, if the circumference of that circle is 2 pi, then we measure the radians to say that to go a full circle 360 degrees is exactly 2 pi radians. One of the nice things about that is if we wanted to talk about what's one rotation of a circle in degrees, 360. What's a second one? 720. Do you know what a third, fourth, and fifth one is? Well, it's 360 times 3 times 4 times 5, and we would have 1,080, we'd have 1,440, we'd have 1,800. But it starts to get hard to figure out with mental math how many degrees is a rotation of 7, 8, 9 times around a circle. The nice thing about radians is that a full circle is 2 pi. So 2 circles is 4 pi. If you want to know how many radians it is to go around a circle multiple times, it's going to be 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. It's much, much easier to calculate. And if that makes sense, that a full circle is 360 degrees and the diameter of this, the circumference of this circle is 2 pi, then the measure of the angle that's equivalent to a full rotation of 360 degrees is 2 pi radians. If that makes sense, then cut both of those in half, 360 divided by 2 and 2 pi divided by 2, and over on the left-hand side, on the x-axis in the negative direction, is 180 degrees, but it's also pi radians. When you look down at the bottom of this screen, you'll see that on the study tip, 180 degrees equals pi radians, and therefore we're able to have a conversion where if we want to get from degrees to radians, we multiply by pi radians over 180 degrees. If we know radians and we want to convert to degrees, we multiply our radian measure times 180 degrees divided by pi radians. Let's see how that works out. 180 degrees equaling pi radians is really the linchpin. It's the Rosetta Stone. It's how we get our conversions. If we want to be able to note where increments of 90 degrees are, 90, 180, 270, continuing around the circle, well, 180 divided by 2 equals 90, so pi divided by 2 is where we're going to have 90 degrees. If we come from 90 down to 180, then we can keep going pi over 2 to 2 pi over 2. That reduces to pi, and that's where 180 degrees is on the x-axis. If we go down another 90 degrees so that we're at the y-axis in the negative direction, 270 degrees, that's going to be 3 pi over 2. And if we come back up to the full circle, that's 4 pi over 2, or simply 2 pi. Note where those are on your worksheet. If we turn our attention now to 45 degrees, we can ask ourselves, well, how do we get there? And the Rosetta Stone, the pi, would say 180 degrees divided by 4 equals 45. So pi divided by 4 is going to equal 45 degrees. You can do that from pi. You can also do that from pi over 2. If you divide pi over 2 by 2, you wind up with 45 degrees. You wind up with pi over 4. So let's walk around this circle. We have 45 degrees at pi over 4. Then 2 pi over 4 reduces to pi over 2. That's 90 degrees. And then 3 pi over 4. 4 pi over 4 reduces to just pi. We see that. 5 pi over 4. 6 pi over 4 reduces to 3 pi over 2. 7 pi over 4. And finally, when we finish our circle, that's 8 pi over 4, which reduces to 2 pi. If we look over to the right at 60-degree increments, let's remove those 45s just for the sake of cleaning this up. But to begin with, if we have 180 degrees equals pi radians, 180 divided by 3 equals 60. So in pi, it would be pi over 3. 2 pi over 3 is over at 120 degrees. 3 pi over 3 is 180. That just reduces to pi. 4 pi over 3. 5 pi over 3, and by the time we get back up to 6 pi over 3, that reduces to 2 pi. The last increment we want to go with is 30 degrees, and so you can see that we've got 30 degrees, 45, and 60 degrees. That helps to understand why we were dealing with the 45, 45, 90 triangle and the 30, 60, 90 triangle. Let's see where all of these things fall. Again, I don't have the 45-degree increments in here written out. The points are there. But how do we locate 30 degrees? You have lots of options. You can say that 180 divided by 6 is 30, so 30 degrees is pi over 6. You can start at 90 degrees, pi over 2, and say that we're going to have to divide by 3. You can start at 60 degrees, pi over 3, and divide by 2. So we wind up at 30 degrees. And if we walk around going from blue to red to black and keep going around, we have 1 pi over 6, then 2 pi over 6 reduces to pi over 3. 3 pi over 6 reduces to pi over 2. 4 pi over 6, 5 pi over 6. You can see how the progression develops. And anytime we have the ability to simplify, we do. So just as an example, 10 pi over 6 or 5 pi over 3, that's the same as 300 degrees. We refer to that as 10 pi over 6 just so that we have our reduced form. So over on the right, you can see all of those values there for both degrees and radians for one revolution in the positive direction around the circle. We can continue on, so we have 11 pi over 6, 12 pi over 6, 13 pi over 6 would be coterminal with pi over 6 because 390 degrees would be coterminal with 30 degrees. We can also talk about locations, meaning what are the coordinates, but that will be for another discussion. Now can we convert between degree measures and radians, radians to degrees, and can we get a quick little sketch of what the diagram will look like in standard position? For 225 degrees, if we want to convert to radians, the rule is we're going to multiply by pi over 180. Notice that there's degrees in the numerator and denominator. Those are going to cancel out. When we multiply, 225 and 180 reduces to 5 over 4, and it's traditional that we're going to leave pi in our answer. When we sketch that, we're going to be down in the third quadrant, 45 degrees below the x-axis, or pi over 4 below the x-axis. Negative 450 degrees, again, we multiply by pi over 180 so that the degrees cancel out. We're going to wind up with negative 5/2 pi, which is to say negative 2.5 pi. If we were to go from standard position in the negative direction, 1 pi would be a half a turn, 2 pi's would be a full turn, and 2.5 would get us down along the y-axis, a quadrantal angle. We would be in this position. 7 pi over 6, now that is a radian degree, so we multiply by the reciprocal, that is 180 degrees over pi. Notice now that we have pi in the numerator and denominator, they're going to cancel out, and we'll be left with that degree symbol. So 7 times 180 divided by 6 gets us to 210, and you can see where that's located. Finally, negative 12.5663, that's a radian measure, and you can tell because in examples A and B we have degree symbols. Now we do not, so we just simply multiply by 180 over pi. And I know that it doesn't look like the pi's will cancel out. In this situation, we just go straight forward, multiply that negative 12 times 180 divided by pi, and we come out to negative 719.99. That's really close to negative 720. That is really close to having 2 full revolutions. Our initial side is along the x-axis, and our terminal side will also. Thank you for watching. I hope you feel relatively comfortable with angles that are in standard position, having their initial side on the x-axis, the vertex at the origin, and converting between degrees and radians. In our next lesson, we'll talk about arc length and area of a sector.